Alright, so I'm going to record this real quick. I'm not sure what's going on out there. The window open. Suppose I should close it. Alright, let me just do that real quick. Alright, okay. So, this is going to be a more lengthened video. I'm going to record this for a long time, and I'm going to be only using words to describe everything because I don't have any pictures to give you. I don't have any CAD designs. I still need to work on CAD designs. I need to get involved into computer aided design, so that way it's far nicer to look at, and you might actually stick around. But if you can stick around to me talking for a while, I must warn you, I have not slept nearly enough in the last 2 days, thanks to having obligations much earlier and not having the ability to change my sleep cycle. So I'm operating off of 4 hours for the last 2 days. Not great. So, alright. Warnings out of the way. Please hit the like button. Please subscribe and follow on my social media accounts or here on YouTube. And let's get this started. Let's start with the valve upgrades. Alright, I've talked about them briefly in the past, but I have since revised a large amount of what it was I initially talked about. They are now going to be, think of in a sphere, angled valves that actually cross at a center point in that sphere. Okay? So that means they're at a diagonal inwards, alright, to each other, and then they go into the end of the head. The head is now a hemisphere, okay, or hemispherical. Alright? Now, these are valves that have a heel, okay? Think like your shoe, there's that little heel in the back. Alright, now they're angled at a very obtuse angle, okay? Now, they're still a straight valve that happens to taper to, which I'll get it into a second why this works, because that heel, a good way to go into it really quickly is the heel slides into the head area and seals with a little bit, because it still has a lip on the outside of that heel, and so that will allow for it to be still a perfect circle, large diameter here, okay, right? But from its perspective, it looks very much like an oval, even though the valve is a circle. All right, larger diameter because we're coming at a much steeper angle, and they are tapered to a point at the top. And so the bearing journal can either be tapered to wider to then smaller to where the heel of the valve is, where it's connected, and then it has runners, so parabolic curve, little uh, channels, grooves that run into the valve. What that means is that it's cooling the rear, which is already got like that heel there that'll slide into, and it's very sealed as a result of that, and it'll skip over the little lip there into that little channel area, which is a little lower than that is anyways. Okay, caveat being is that there's very slippery ceramic there, and then there's a millimeter of insulative ceramic at the bottom, and then the valve is vacuum insulated, meaning it's hollow and there's a vacuum there. Alright, now it's still regular sized, valve, but as it closes, because it's tapering to a point to where it then widens into this heel area for the valve, that allows for me to have that flow a lot nicer, because it's skinnier there too. It allows for that air behind where that is to then skip into where the valve's heel is, because that's a way for me to also have a little journal there too, like a little bearing journal. Alright, now it's still a round, perfectly round circle, but from our perspective it'll look like an oval, because like it has a higher degree of curve to the direction of airflow and travel. That's from the port and ported to be curving into that angle. Now, the reason why we have it on one side like this is because the port then acts like a short velocity stack. Alright, so it's a parabolic curve funnel that then goes into this valve area, which then has the heel help channel it and flow it into, and because it's at an angle, and it's with it, take your hand, okay, here, and then angle it down, alright, at a diagonal. And then that's where the valve is with the heel, take your other hand, and then that's where the angle is for your arm for the valve. Alright? And it's like that allows for when it goes in, as it funnels in, it'll travel down and skip off the side walls of the cylinder. Alright, now same thing with the exhaust. The exhaust is going to be smaller, but still going to be much bigger because I have a much larger area to put this into for the head that ultimately allows for those diameters to be much larger. And same thing for the sealing, because it still seals up to those areas, right? But then it opens up, so I have a much larger duration, and that curve, that obtuse curve, is what allows for it to suck in. But they are not facing the same way, they're facing towards the cylinder wall. Now what this does for your aerodynamics, for your intake and exhaust, is means you can gain scavenging that's much better. Okay, so you can cut in on the intake side of your exhaust and the exhausting side of your intake. So I know, weird concept, but imagine that's the intake coming out from that intake valve. So that's the exhaust area, right? That allows for that to be such that it's angling in, curving down, and then scooping out that exhaust, and then it's scooping it into your exhaust. And so since they're opposed on opposite sides of these valves, okay, that means one side it has to travel much further around, thus introducing more vortex and a higher degree of aerodynamic flow, velocity, which is mass airflow. It also cools that top quite a bit more, so that way you have less likelihood of knock, which is a big deal. Now, if you're a carburetor setup, you might not want scavenging. In fact, you never want scavenging, is a better way to put it. Like, you never want to do scavenging. But this, you can do lower RPM scavenging at a higher degree of efficiency, and because you have port and or direct injection, these valves now allow for you to scavenge with a greater degree of efficiency and higher degrees of volumetric efficiency, which improves both the air pressure in your cylinder, the outright air-fuel mixing because it vortexes, and then the degree of combustion is now better. Now, this is the valve idea, alright, but we're not done yet because this also has to deal with heads, alright, and so I figured I might as well go all the way. Instead of a camshaft that has to have these roller rocker arms to be able to make this work with springs, I was like, alright, I'm out. I want a single solitary camshaft. One camshaft. I don't like dual overhead cams, and I want to sink it right next to where these valves are anyways. So they're going to already be there. So I found that if I take a hollow camshaft, which they don't make those, so I had to figure this one out myself. So so let's start from the beginning and then we'll work our way there. Alright, so we'll take the camshaft and now it's hollow, right? But now it's not a camshaft, it's just a tube that fits into the camshaft area, which then has another tube that has bearings that you attach, alright, into that. So it's like you seat this with these bearings, and then you seal it on either end. Now hold your horses. We're going to put hydraulic fluid there. All right, now they have a specific size, meaning 50-50. And what does this do? It means that I have them separated. I want them separated. But as it spins, the outer camshaft, which will have, wait for it, okay, before you say no, gear, all right, teeth on the outside, right? But again, hold on. You have to give me a second before you race away CAD design or something else. They're vertical, okay, lines in certain areas for with little holes to suck in air towards the center. These are now going to be our version and design of a heatsink. Okay, but I want those holes to pull air in and or oil in and then fling it out to take away the hydraulic fluid's heat. Alright, we're almost there. On the outside of those fins, you're going to have the gear teeth there. Now, in between that gear tooth and the gearing of the lobe, which has to spin, so this goes over the bearing area that this tube slides in, alright, we place in and bolt on after drilling and tapping and welding is personally after bolting it in is what I prefer, but you don't technically have to. But anyways, that is where we place in the bearing for the lobes, which are just gear lobes that work on the sides. Then there are going to be markings and indicators on the side, okay, to allow for you to know for a regular 4-stroke with, not the medium high, it'll just change timing, which I'll get to how that works, and I'll get to how advancing and then increasing duration or retarding, or as well as lift will work. Give me a second, I have lift here too. Okay. Now, these, where the lobe is, can move out and in. Now, the outer side of this camshaft can slowly open up. It will slide, but it's sealed. Okay, so it's like they're like lobster tails, but then they're sealed like very specifically. But there's a degree of pressure. It means that the faster it spins, it has to overcome a degree of pressure for it to open up to its full width. Okay, just like any other clutch. Instead of springs, though, we use hydraulic fluid. So hydraulic fluid getting pumped out until eventually, through little holes, or you can widen the holes, and that depends on what you want to do. It'll come preset for certain RPMs, but you can ultimately change that yourself. And so it'll eventually have that restriction completely removed, and then hydraulic fluid will go back in. It will fill back in those gaps as it slowly spins down. Alright, now what that means is that it pushes, because it's still, from our perspective, well, any perspective, it's a slidey part. So it has lubricating oil from standard everything, oil goes in for our heads, so it already has that. But what it means is it slowly pushes that lobe forward on the thing that it spins. So it's just the thing that it spins is getting pushed forward, and it doesn't interact with the lobe on the other side. Okay, so that means it just moves that forward, but it'll eventually go back, okay, as the size of that. So there's a spring there. In this case, it's, again, hydraulic fluid. As that opens, that pressure then goes into that other area, and then that pressure is overcome by the spin of the tube, all right, and then eventually that has to go back. Alright, so that's its own version of a hydraulic fluid shock spring, basically. So it's a reservoir. It does happen to have a, a diaphragm of a spring, which is just like going to be cooled on the outside with the oil, right? Anyways, I didn't talk about that before ever. I've never talked about any of this, I think, completely like this. So hold your horses. I know it's already 15 minutes long, and it's going to be longer because I'm going to describe a crankshaft upgrade and a spark upgrade. So give it a second. Right. Now, that pushes it back at a set fixed rate because, of course, that's a shock. So it's very consistent one way and the other way. Now, that lobe is changing based upon a cone gear, is what I call it, but then that's not what they apparently call it. Anyways, it's a gear that's shaped kind of like a cone. Anyways, that allows for me with a solenoid, there's going to be two of them, and rods. One just goes forward and backwards. Another one goes forwards and backwards and can rotate either clockwise or counterclockwise because it depends on how you have to put it into your vehicle, either towards the front or the rear with the heads, but it's still the same rod, so on, so forth. Right? Anyways, the one that moves forward and backwards and just does that, that changes the gear. It moves it forward and down, right? So it's really just down. But like that changes to a wider or a lower, depending on how you want to set that up. Right, and that can advance timing if you have it from larger to smaller. But then, hold on, right? Because we're not done yet. The other one, it goes inwards, and it rotates. Now, inwards pushes down because this is going to be the big change. The hydraulic ram, because there's a little reservoir that has a tube that's the direction of travel that you want it to go, and then a return line tube, and then a reservoir that has, from the reservoir, that's two separate reservoirs that's cooling the hydraulic fluid, but it doesn't pump it. There's no pumping. It's static pressure. I just want to keep the pressure consistent from that reservoir because that's our heat sink. That's our reservoir. And then same thing with the reservoir that is inside of these tubes. Okay? Now, the other side is slightly lower down, meaning it's a little further away than the intake, because that's the press it in and it goes back up. Yeah, it stays where it's at, and then it will go back up with the next press in from your lobe on your camshaft. The valve, okay, so there's a return, so, because like anybody knows, push rods will throw forward the rod and it'll keep going. Well, there's a valve that you change where it ultimately is with that twist. So when you push it in for the moving forward and backwards and twist, it moves further away from the next inward push, and then it'll move closer when you move it out. Now the twist is just a valve on the tube. That's the reservoir side. So like that shifts it on the pressure plunger, which is a hydraulic ram, and it moves it further up or further down. What that means is that's your lift, because it'll keep trying to throw it forward, alright, and you already have lift based upon your solenoid going in, and that pressure, or not the solenoid, the gear being pushed. It's gears, a slider basically. It's a slider, but then the gear also adds a degree of lift when you change your timing forward. So it's like advancing your timing, and then it also happens to increase duration as a result of this. So you gain lift, duration, and advanced timing, all of which you want, and it's dynamic, but it's not infinitely variable. It's very, well, I mean, it technically is, but we're talking about such small, subtle things that I don't think that's infinitely variable. Just deal with it. So, It's like you have a minimum and then you have a maximum. And then like there isn't a lot of variability there for what it's worth, but then you kind of do. You have modes. So anyways, the gear changes, but then that also presses it in as it moves inwards as well. So it changes its advancement, but then it increases its degree of duration, alright, as it moves the valve as well. It's like these are two solenoids, so you can essentially advance timing. You don't have to change duration, and you don't have to change your lift. But since it's already changing your lift profile and you're now advancing, okay, because it's widening as it goes longer, that will also happen to have that neck. It can stay, so you increase lift, so you advance and then you increase lift, right? But then as the gear and the valve changes, then it'll move itself further, all right? So, it's a good way to put this. All right, so lift moved forward because it slid on the rail that the lobe is on, forward. So it plunges more with the angle that it's moving at the valve, because these are the valves that cross diagonal valves. So it moves forward and it pushes it in. And then the downward part, of course, that's its push it and return it back. Now both of those have valve areas that have to move back because it'll try and keep moving it forward, and so where that valve ultimately goes is where it will really very much try and stop because all the pressure is lost right when it's there, and so it can't move further. That then goes into the reservoir to get cooled because it takes a degree of pressure and heat to do this. And then that, after the reservoir gets filled, that pumps it, and then that returns it to the other reservoir, which is then there to suck it in, to then get plunged. And so when you plunge it down on one side, it's going to plunge it back up, okay, for the hydraulic fluid to be returned back past where the valve is. That acts on the other diaphragm valve here that's on the valve stem, because that's how the hydraulic fluid pressure rail setup works. Now, one camshaft, because these can be ground very small, you don't need them to be very big. They can be very small, so they can be very close together for the lobes. But it's like I'm talking about grinding it because it can be very small, because I can have that also be my exhaust. One single lobe can both be intake for both the down and in, and you can change respectively how fast that occurs for both and how long it stays around thanks to the timing and the lift as well. So I got all of them, but those two solenoids also mean, because it moves forward, well, it moves something down or back out. So like back out means that's another version of, for the exhaust side, if whether or not you want it to, because there's a gear for that too. You can have that one, which is just a round gear. So it's like that one can be a cone gear, which I call it a round gear because it's more like a ball, like a sphere gear, spherical. Anyways, it doesn't really matter. Point is, there are a couple of gears, but types that you can choose from. It means that you can have that go further back or further forward, and advance or retard, and have increased duration or increased lift for your exhaust as well. Which means you can get much better scavenging effects, and that's also why I have different areas of where the placement of your lobes are for regular. Then my dog's playing with the squeaker toy, of course. I'm sure you heard that. I have earbuds in. I didn't even hear that. He just dropped it right by my feet. Okay. Alright. Alright. Thanks, Phaser. That's my dog's name. Anyways. Alright. That will also be able to take care of your exhaust, but it's the two for the gear change, that is. I'm trying to caught back up because I got distracted. Alright. So that changes your scavenging. So it can go from a regular scavenging that's at high RPM, and then a medium, as low as medium RPM scavenging advancement, medium RPM, where it'll start to actually occur. All right, and then all the way to two-stroke advancement, which is where you'll place the rams placement in the thing that you place over the bearing areas. Okay, that divide all that stuff. Anyways, think like an arch, and then like from each one of those things, but then also there's like the whole rail system for the plungers and so on. So right, that allows for you to gain a two-stroke, but they've been calling it a one-stroke. Although I kind of understand because every downward stroke is a power stroke. You know what I mean? But then like that's apparently not how uh, you know a one-stroke works, because you still have compression, right? And so that's what that is. But then at the same time, it's like I can see why they think it's a one-stroke. And truthfully, to a regular person, it wouldn't necessarily not be. But if you have a single one on the bottom, like a single another combustion chamber on the bottom, then you gain a one stroke. Like, because that's basically all one stroke is. It's a never-ending power stroke on both directions, which is pretty powerful. But anyways, this is not that. This just allows for better scavenging and much better two-stroke scavenging as a result, while having port injection, because the heads that I thought about designing have port injection not into the little air intake manifold. Instead, they're actually drilled, because that's the whole plenum, or the short velocity stack that's now the port because of how far it has to travel. And so it's like that's where the actual injector is going to go, right? And then I have a little plenum, so then I put an extender piece, which has four, yes, phaser, I know, four given detectors, sensors, detector, sensor, whatever. Heat, meaning temperature, pressure, humidity, and volumetric flow. Those four give us, with the right calculations, and we know already ahead of time the nozzle size, okay, which is the valve size, and then the flow rate, which will increase by the time that opens and scavenging occurs, a given change to our fuel map. Okay, so injectors will start after that's, well, before it's actually closed, because it still takes time for that fuel to get in there, even though it's short in terms of its duration, a few milliseconds. A few milliseconds means that exhaust can still be open, and I can gain that increased advantage of extra fuel for the given extra air I gain from this. Yes, Phaser, we know. Squeaky toy. I have a pretty high up bed. It's so adorable watching him just try and jump, and then he fails and he's just like anyways, yeah, moving on from that. That's basically the entire head described, because you have both the intake and exhaust, and then you have the ability to change your intake and exhaust scavenging in terms of your desired power output and setup, okay, for your given engine performance. All right. Now, the heads, I got tricky with it, because I was like, well, there's a way to 3D print and then cast, and then kind of forge, and then temper, and all this other stuff for a two-piece and then welded two-piece construction of this head. So it turned into, how Formula One engines have that little chamber that it goes into, and then they spark ignite that. Well, think about that, but across a lot of different areas of the hemispherical part of this head. But instead, the spark plug is actually it slides in into like a corkscrew design or whatever. But anyways, it now has that as both the ground and the connector. So that lead, that connector, that electrode goes into multiple little areas which have their own design of coils. Now, a way to put this 3D printing, which isn't really 3D printing, so I'll get into it, but it's like the nozzle happens to have a pressurized gas, like a noble gas, that's a certain static, all right, and then we're gonna heat it up using electrodes, effectively, that go to a ground area. All right, that makes it positive, but then it's like we're also heating it, and then we're also pulsing it, and then vibrating the head. So if we change the nozzle size while we're vibrating it and pulsing it, then that allows for a very specific type of uh, tweezing, optical or pressurized tweezing. So like air tweezers, pressure, sound tweezers. But then it's also a thermoacoustic pump, and then if I really ground it out and then really give it some good, electricity, I then am able to really have it, just like powder coating, stick to that substrate in a very, very, very tightly controlled manner. And then I can allow for a degree of heat, either with lasers, which I typically use lasers, IR or something similar, that then vibrate it and then stick it with, of course, this is either in a vac. Again, it depends on the materials here that we're talking about. So it's like powder coating, but then supercharged, but then it will eventually turn into a plasma deposition. So give me a second. All right. So it's a near vacuum, and we suck out that air as we are putting it in, and that increases its flow and directionality depending on where the substrate, because it has little holes in there, and then those are also where the grounding areas are, and then we have like the direction of the nozzles and the sound tweezing that we do, along with the lasers helping really specify its optical tweezer characteristics as well by confining it into a very specific area. Now these nozzles are fairly large, same thing with the canisters and everything that we're using, and same thing with the area. And eventually those holes get taken out, and then it turns into a plasma as it gets hot enough, and then I'm able to deposit the plasma. Now the plasma dumps its heat because it has heat sink underneath of the deposited, kind of like a powder coat layer. That allows for, with the ground substrate and then the air pressure moving and the plasma deposition cooling and heating, which we can dump in and then pump it out with the correct pulses. We rapidly heat it up and then cool it, helping create a version of quenching, and then we have normalizing, and then we have quench, and then we can, as it vibrates that bottom part, as it's still relatively warm, it allows for, with the correct electromagnetic part on the substrate and then the nozzle head, a alignment to along with electrostatic degree of polarity alignment of the given material. Instead of creating a magnet, though, we're more looking for allowing for crystals to form, and then as they reduce their heat, as we cool it, then we take that out, and we have very specific dimensionality to that. So we can only do it up to a certain distance, and then we have to leave it alone. And so it's like it gets rid of porosity, because it does, but it also means that we're removing forging issues, because we're kind of forging. We're not forging, but we're kind of forging, we're kind of tempering, we're kind of quenching for hardening, and we're kind of doing a lot of that because of the microcrystalline structures that we can try and align. And it all depends on, like, again, this different, aluminum, steel, ceramics, gems like zirconiums and so on, for increased variability in strength and structural designs, because we can have up to a nanometer size of deposition that's very quickly placed down. Again, these would be bespoke heads that would be designed for these spikes. Now these spikes are a little different. They're cones. Think like bell ends, but then they have like a little cone that's on the center that's hollow with stators that then also takes that center part and then fires it more as a jet towards the center and then the cone around it. Now, if I do it correctly around this area, which we haven't gotten to the casting part, so give me a second on the casting. Hold your horses. I know this is a huge upgrade for manufacturing, all right, but it's also cheap. For what it's worth, like making those little electromagnetics and electrostatics and stuff, actually, we already know how to do it, and they're cheap to make and manufacture and put together for this kind of a system and setup. And they're not meant for something that's super, super, super big. They're meant for like a quarter inch, maybe half inch at most. Okay? So this half inch at most turns into then getting welded later to this cast part that I'm going to put together. Hold your horses though. I have a mold. So I use solar, okay, and then constructive and destructive interference. So we'll take radio waves if we can, or ultraviolet and natural light, and then we'll try and break them down into microwave and IR radiation. All right, electromagnetic radiation, light, basically. Now, that gets laser reflected, and then there's a bunch of like two-way mirrors. Effectively, it's a mirror on the inside, and it has mirror on the outside. So, give it a second. Now we're gonna get it really hot. We're not gonna get it to melting. We don't want to. We don't care. We're gonna use thermoacoustic pumps. So we're gonna use acoustic pumping, and then we're gonna keep one side much hotter, and then we're gonna dump more of that IR and so on. But this time it's in the mold that it's already more or less formed as a block. All right, as we're heating it up, we're gonna start vibrating it into the mold, and it's like we're using hydraulic presses, and then to form the beginning of the mold as it heats up and gets easier and easier to do this. Now that we'll start with like a stock aluminum, okay? Stock like just literally basic 99%, simple aluminum. That's it. Really pure whatever aluminum stuff. All right. Now, that then gets slowly compressed, right? Which is not too bad. Then we're going to dope it. We're going to make an aluminum alloy, and then we're going to have doping like the zirconium ceramics and gems and so on, that kind of stuff for different elements to make not just a aluminum, we're making a metamaterial aluminum hybrid aluminum and ceramic composite. All right, which is a metamaterial, all right? Makes it lighter, stronger. No, it definitely has a fatigue limit now, and it's less susceptible to heat getting into our valve port areas, because we're going to make it really small. Instead of making it much bigger, now we're going to have different angles where it'll go up or directly perpendicular for obtuse, 90, or acute angle. Hold our horses. We're not melting it yet until we get to that pump, the acoustic pump, that then after we've kind of put it into the basic shape, we're then going to melt it, and there's going to be reservoirs with that heating using the microwave and IR and the acoustic pumping for increasing heat in one area, so that part will melt. Those go off into a reservoir that contain the doped materials. As we allow for it to squeeze back in, all right, with just basic hydraulic ram, then it squeezes in. We use vibrations, which is a fancy way of saying, so we have the acoustic pump keeping it still hot, but then we're going to have it squeeze and undulate to basically mix, and then we use another vibrational method to create cavitations and sustain the cavitations as we move the acoustic pump to another section to start that process. So it cools it off, takes the heat away. We use another acoustic pump to basically transfer the vast majority of the heat from the liquid that once was to the other area, while still heating that area again with natural sunlight, IR, and reflective and all that stuff. Right. So that allows for us to create little cavitations with reflective properties towards the inside meaning one direction, hot side. All right, but then we have the right cavitation, but then also not just cavitation, we have that structure, which is a smaller hole to a larger hole in the rear, which means that reflective part then goes and then constructively interferes as it tries to reflect back towards the hot side, whatever IR it might have, and that's an insulation of vacuum insulation, and that's ceramic in those areas because of the acoustic vibrating pumps that we can change the density of those materials, thus making insulative materials there, and then doping of that area. And so it's a whole bunch of pumping of a liquid and then cooling it rapidly, and then we still have the electrostatic and electromagnetic to create alignment and strengthening as we compress that, by the way. So we're going to compress that area. Well, it's still hot, but we are going to compress it slightly as it cools because we had to let it expand. And so that, but we're not done yet. So we're going to go through all of that again for the rest of the entirety of this head. And so it has to be insulated, and it's going to ultimately make it such that the intake ports and exhaust ports are separated and insulated both via a ceramic insulation and vacuum insulation with a reflective property of like a mirror system and the correct holes, so we have structure that it attaches to, but then those holes then make it such that they reflect and bounce the IR back towards the holes inlet, if you think about it like that, like a quantum slot experiment. So it expands and then polarizes with these little lines on the inside and then reflects, blah, blah, blah. Point is, it pushes more IR back towards the hot side than it does the cold side, and it's still vacuum insulated anyways. So we're done. Because there's a cavitation and there's no air. So cavity means no air, which means vacuum. All right. So that allows for that intake and exhaust to be extraordinarily close, while still having the bearing basically right next to them in between, which is its own insulation. Part two, which then you put your bearings there, and then you have like the little, overhang arches over that, right? And then we'll have covers. I'll get to the covers in a second. All right, and they can be specifically set up with the bottom that we just talked about, how I'm going to make and manufacture with the 3D printing design. That thing goes into this. So we're going to, before we're done, this is going to be over, okay, so like, meaning made to oversized specification. So this is going to be heated up into the mold, or place it in. It's still warm. We're going to vibrate it, and then we're going to use some electricity to basically weld those both together with the heat, and then we're going to squeeze it with the hydraulic ram pressure to the correct specification of size, and then we vibrate it and then let it cool rapidly, and then we heat it back up. So it's like it's already pretty normalized. Then we squeeze it, and then after we've heated it up, and then we're rapidly cooling it around that time, and we're vibrating it throughout. So we're going to make, with the electromagnetic and electrostatic and the vibrations, a forging of this piece of metamaterial now. And then the larger vacuum and all these other, so they compress, it removes porosity, but then that vacuum area also cools more rapidly because it's thinner, and so like that draws out heat to the larger parts that are cooling. So then it squeezes and it maintains that vacuum area. Of course, there's also the vibrating part that helps that process along by keeping the cavitation there specifically for this to be pressed in that way, and then that forges it and hardens it, and then we let it slowly warm up again and then cool off slowly, and then we do that a couple times, and then now you have a forged metamaterial head. Alright? Luckily though, the heads cover real easy. That was, by the way, the whole like mold and everything I talk about already have these designs, like or versions. Like we haven't put them all together, but like these are all known to work already things, and so we're just piecing them together the right way to get more out of it. And so they're cheaper, but then as a result, I don't have to spend like millions of dollars to get like this super hot pressurized molding system. Instead, it's more of a forging, molding, all this stuff kind of system that's together in one that allows for it to all do this. And for me, it's like, well, no, it's cheap. It's cheap to turn something else that's like a regular caster into this because we just need the right ceramic on the inside and then, graphite or whatever mold to like try and handle the heat. And then we can replace that every so often. So cheap. And then same thing with the ceramic. It would be insulating ceramic, but then electromagnetic fields and electrostatic fields extend further than their skin where the ceramic is. And the ceramic can still handle that as long as the electromagnetic coils are able to be something that can handle the heat and still have electricity run through it, which is fine. We do have that as well. All of this will work. The vibrating part is its own version of spinning electric motors that can, like an impact wrench or similar, create those versions of acoustic pumps and thermal acoustic pump, meaning it's going to move heat in one area or another because it's a pressure wave, and so like it'll end in one side versus another. And we use it as a gas typically, but when you use it in a hot spot or a hot piece, it still produces the same effect. So we got forged, and now it's welded, but now it's really just one whole piece, and so that then allows for me to have those intricate little, spots which have the coils, and then they're not very big, but then they have much longer tubes in multiple spots to allow for that air, and so like it's a lower compression value, but then it's like going to be closer and flatter even if it is hemispherical. And so as a result, I gain an advantage again in terms of allowing for multiple spots of burn that then gets thrown in towards the center. But hold your horses again, the spark plug goes into this spot, which is the lead connector that then goes into all of these other spots, so that spark plug never actually enters. It's all of just these spots where they go into these chambers and then ignite, which is now we're getting into the spark upgrade, the spark plug upgrade. Finally, we're getting into the spark plug upgrade. So this is a really cool spark plug upgrade. It comes with an ECU, capacitor bank, and then the coil. So these are both grounds. So like the stators and the cone for that chamber as it races out. And of course, it's like there's a certain distance, and then there's a certain amount of compression, and a certain chamber size. Basically means from 70 to about 150 octane. It can handle up to usually around that 100 to 150 pounds of boost. Okay, so like should be good. Now, hold on to your socks here, because we're about to talk about how plasma, like a neon transformer, and how spark, which is not quite as high voltage versus high current draw, will ultimately work. So we're going to create a high voltage in multiple spots using that spark plug, and then a couple of other coil packs that dump into, which are inside the head, which dump into this, okay, which are kind of like micro coils essentially, but then they have their own version of, they're insulated and then ground that are built in this, because of course we 3D printed and then basically weld it. So this one is hot enough, but then it's like it's not really going to cause any problematic stress factors. It's a good way to put it. It's like it's welded, absolutely welded. Okay, so that's good. But two different materials almost, You know what I mean? They'll bleed into each other, so they're welded. One real forged piece, basically. Lighter now too, because I don't need to use the same type of materials, and I have a fatigue limit, so it won't go past that. All right, great stuff already. You know, lighter, stronger, all that stuff with insulation for heat and cool things, right? The caveat here is that those little coils have to be wound around the tubes. Okay, same thing with the ground and the leads, which has to go back to something, usually, and so like that goes back into its ground. Okay, but like it usually loses a lot, and so I didn't like that, and so those tubes and so basically are the version of a ground, and so that will go over into a bigger, thicker ground lead, which is where the actual exit for this capacitor bank is going to go to, which is the new electrode for creating large amounts of current. So now we got a spark initial, and then after it starts firing large amounts of these pressurized jets effectively in towards, and then burns towards the center, it creates a high compression in a sphere, usually towards where the piston head is, which creates compression ignition around there very consistently. But then in the center, in a sphere, or roughly oval egg shape, it'll create a detonation. But because it's already traveling down, which I'll get to the crankshaft in a second, but think about it like this: the crankshaft's going to be fine, like the wrist pins and all that will be fine. As the spring of that pressure wave then gets moved outwards, and then it mixes as it moves down, and so it creates a degree of higher static pressure that then rebounds and then goes back down. So it absorbs a small amount of detonation, a small amount of compression ignition for the vast majority of its spark ignition. That is a big flame front around it. Okay? So it's a much more complete burn, much more consistent burn, and then as it's going down, we start immediately drawing a shit ton of current with the capacitor. We dump it into the capacitor. All right, so it's like we're going to rip out as many electrons during this process as we can using the heat and pressure to try and really remove that, and we're trying to break bonds. All right, and so by the time it goes from its top dead center and it moves down to that initial spot, after it races away a little bit at first, which is why that detonation is kind of a cool little spot, it then turns into, well, we then try and make a plasma, like a neon transformer. We try and make a plasma, and it dumps into like this capacitor and all these other things that try and make this happen. So we have a regular alternator. We don't alter the alternator. We have a regular battery, but it's like this slowly builds up this capacitor and battery bank, so on. All right. So I didn't talk about the battery bank, but I figured, I wouldn't need it. Just on the safe side. Anyways, you wouldn't really necessarily need it, but the point is, it's like it goes in. We try and take those electrons and make an electron flow battery with the capacitors, because it'll go through the coil and then dump it into the capacitor banks, which are going to use like a couple of, and then anyways, point is, we've got the correct electric rectifier setups, and we're going to use energy to do this. So you have to use energy to draw this, to create a given amount of plasma. Now then the electrode that's on the center of that tube in that chamber, and then the stator area, are both versions of electrodes. So when we pulse them with the setup, because this has its own version of a pulse system, we then dump back those electrons and to crashing out the plasma into a regular, exothermically able to react much more readily under higher heat and pressure than before, with now more freed up oxygen, because it'll take N2Os and break them out into N2s, and then CO2s will turn into COs, but then COs will then turn into Cs, and then H2O can turn into an H, and then an HO, or an H2 and O. which means we'll exothermically react back again, and then as it's racing away, and we dump in electricity to increase our heat yet again, because we're taking heat in to create that plasma, then we made it. But we also made it much more efficient because we already had heat and we already made it electronic. The electrons are more excited already, and so as a result, that makes this whole process easier. Okay, but when we pulse those two different versions and we use the coils that are there, we fire in electrons effectively all together, much like the burning combustion gases. It'll allow for us to fire in basically plasma electron bolts essentially into the combustion chamber. But then that allows for it to crash out in a specific way that tends often to remove a lot of the nitric oxides and carbon oxides into carbon dioxides and regular water, and there should be very little bit of the O2s left, but O2 will be higher because unless you happen to increase the fuel to try and match that air fuel ratio, because you will be doing this from the nitric oxide now freeing up oxygen, then you gain that increase of exothermic reactivity as it travels down from that initial movement to now an even greater degree of pressure and cleaner burn. So we have a greater amount for the electricity use and the heat we're putting in to having greater amounts of torque and pressure, but it's a larger volume. Think a much greater increase of retarded timing, and then it slowly crashes out, or very quickly crashes out, but then also exothermically reacts again as it's doing its power stroke, increasing its degree of heat and increasing degree of maintained pressure, but it's in the standard 4-stroke configuration or the 2-stroke scavenged configuration that then has that exhaust scavenging effect, which helps cool that cylinder sidewall, which the cylinder sidewall is still going to get cooled, but that heat can then go into an extra pressure and much greater in terms of complete cleaner burns here into a turbo setup. Now, we're going to get into the crankshaft. All right, because that's the head and the spark and the valve upgrades done. You have your plunger, your hydraulic ram, all this stuff to be able to move this much better, much more easily. All right. Now we also happen to have a really good design for, improving our torque and cleaner burn of our engine, and ultimately, as a result, have gained back for the amount of electricity that we use. Initially, it doesn't have the capacitors completely charged, the battery completely recharged, and like the alternator is going to be the standard. So it's like the ECU that I have programmed, which this is the caveat to this. All right, there's an ECU handheld, and I don't call it a bypass because it's not. It's an upgrade, is what you call it. Like it's you handheld, or in this particular instance, it connects to your original ECU. It then runs and it learns what your engine's giving it in terms of the plenum little force sensor detector, and then it knows from the sent signals from the ECU as to what ultimately is what it's seeing, because it still sends those signals. We send you certain link sizes so that we know that signal timing basically for it's then held in its memory what the mass airflow sensor must be doing, or it's given fuel mapping really, and its timing and all this other stuff that it thinks. It'll send back whatever the engine's doing. So it doesn't bypass, because bypass is apparently from the sensor data into the ECU instead of from the ECU out to this. And so, like, on a technicality, I'm able to get away in loophole bypassing. Now, that is technically its own standalone, but it doesn't know from any sensors at all, and it must know from the ECU what it's doing, and depending on it increasing for gas or so on, depending on what its sensor and throttle position must be trying to do for mass airflow, O2, and so on, it's trying to give it a proper balance. Well, this works off of that, and then it has its own, like, these are the registered injectors. This is the engine it's going to. Then it has the, you know, fuel mapping, and then it has also the timing and everything it knows. So it goes safe, and then it'll learn as it goes from the lowest RPM all the way up to the highest RPM, and then it'll do super eco, which is just eco. Then it will do a dynamic, which is eco dynamic, and then performance dynamic, and then it'll do high performance, which is maxed out. So eco is retarding timings and fuel and all this other stuff to basically get the most efficiency. Just efficiency. It doesn't matter about power. It's just going for efficiency. Dynamic tries to do with eco effectively bang for buck. So it's like less fuel, greatest amount of performance. And then performance dynamic is it will turn off least amount of fuel to be able to give you a little bit more, bang, and greater degrees of timing and everything for the performance aspect. But then when it's cruising and it knows it's cruising based upon cruise control being there, your throttle position not changing very much, so on and so on, it then says, because we go and bifurcate throttle position for that sensor, and instead now it's Valvetronics, because Valvetronics, we don't have a throttle, we don't have that little valve there, so it's like that's unnecessary, so just use the valves, you know what I mean? So like that for fuel timings and everything will be what it runs off of for Valvetronics, where it's its version of a Valvetronics, right? This is the ECU. I already said all this. Moving on. It's like I'm trying to explain this to someone else. Anyways, but that might not understand what it is I'm saying. So, anyways, this then allows for it to not have to bypass and be illegal, because I technically never modified. But then it's like I put new valves on. So, but then, it would know that, black box would know that. Everything to it in its version, it's still doing it correctly. Right? But if I have that go into this ECU and then it goes into that to try and tell it it's doing it correctly, that's an actual bypass. That's cheating that. Right? So that's why I consider that not a bypass. So that means with the increased degree of timing and valve lift and duration and heat and better burn and fuel mapping, all this stuff, it'll know ahead of time, it'll run off of that, and it has to use the given pulses and everything, and so it'll advance its timing and then just use this as confirmation that it's doing it correctly. So it'll go, I advanced it a little bit sooner once the engine started, and it'll go boo boo, it'll be a little bit lagging behind, and then it'll increase it, and then it'll try and match what the engine should be doing based upon its throttle position sensor data, which is bifurcated. So meaning it's split into two. It sends it both to this and to the ECU. It shouldn't be any different. Same thing with the fuel and all the rest of it. Alright, in terms of what it needs for what the driver is inputting for the engine to do. And so this would be its version of a workaround for the ECU telling it ultimately what's going on based upon certain things it tries to do, because it knows what it tries to do, to try and make sure it's running as efficiently and correctly as possible, right? That is the or working back algorithm. It works backwards to know what it's doing, but it already has stored all of the given parameters. And then, of course, high performance is just straight up the maximum as fast as it can get to the highest RPM that you set for it. All right, so like it knows that this airflow with these injectors will only allow for this maximum RPM. You can't go higher. You know what I mean? Which means you need more fuel and you need a little bit more uh, air. So they can only give you this amount of duration. It can only give you this amount of lift. It can only give you that kind of thing because these injectors are too small. It's like if you want it more, you're going to need more fuel. Right? And so goes all of the rest of that. Now, the crankshaft, which is really which is really cool, by the way. Okay, so think for the piston heads, there's a double wrist pin. They already sell those, so I was like, that's easy, simple stuff. And I was like, well, I'm going to offset it actually opposite, counter towards where the piston is. Instead of, forward, we're going to offset it off and down to the left. All right. Now, I thought about the Scottish yoke. All right. But instead of the Scottish yoke, I wanted to have a bearing, and like these are the counterbalances. So think an I-beam, meaning so I actually need to throw that out just really quick. Think an hourglass and then an I-beam. So it's wider at the tops. So take your hand, all right, and then like where your thumb is pointing towards your face, all right, where it's vertical now, and it's as thin as possible, all right. So not palm. Palm is not facing you. Thumb is facing you. It's wider at the fingertips and where the base where your wrist is. All right, and it's round. It's going to be round. Now the center is actually when you then have your palm facing towards you, it's now wider where your palm is. All right, in the center, but then this has its own version of a bearing that has a circle, a sphere really, and then like hourglass cones sticking out. And that's where it connects to the crankshaft. All right, so it's like, why the hell would you do this? Give me a second. All right, this at the top where this rounded part is also has a bottom where it's rounded. All right, same thing at the bottom. Now, this turns into, as it goes up, there are roller bearings into the engine case, or more specifically, this bolt-on to the engine block specifically, that stays in there and it goes up and now undulates as it goes up and down. And it moves side to side, meaning twists. Alright? Alright, so, hold on. These roller bearings move up on sliding journals. Alright, so like Scottish yoke. And then this is still its own version of a Scottish yoke, for what it's worth. So, where it's connected to its crankshaft. Right, so it's meant to move side to side, up and down, and it twists a little. Very subtle amounts of twist. Now this goes into its own sealed little place that it hooks into, and then those little roller bearings that slide up and down, which then have this pivot forward and has an air intake there. As it pivots forward, it seals it up against the top, and then it'll undulate forward, much like, you guessed it, an air pump. It's an air pump. If you didn't guess it, it's an air pump. Think worm as it undulates wide, and then it has a small spot, and then that's how, as it undulates from front to back, it moves forward. Same type of deal, except now it's both the top and bottom, and then also the top and bottom of that top and bottom. And that air pump is now working as a balancer, because it slides on those roller bearings, and then that undulates it with a big, basically like a pyramid, square bottom pyramid, but then those slide into each other. And so as it goes up, it then slides up and then down, and then it seals it to the top. But with this, and this is the cool part to me, maybe not so much to others, but the seal is both not just the gap, but that's also the bearing. Okay, so like there's a gap there, and with the correct gap, it acts as a bearing. And so with the right ridges, it creates a version of a bearing and a seal on that undulation and acts very consistently as an air pump that moves air using the crankshaft as a resistive force to primary, up and down, secondary, side to side, and then tertiary twisting for a cross-plane crankshaft. Alright, now that is a version of a supercharger that I was already going to have parasitic loss for anyways, but now this can be smaller because I have air resistance, and that's also why it moves in a Scottish oak. Okay, well, bearing slidey Scottish oak thing, and that's why it has, yes, oil pumped, and then these smaller areas here at the bottom are the new pump areas, because like that then goes and gets collected for the sump for the oil pump, right? And so everything's lubricated, it's sealed, right? And then now it's an air pump. A supercharger works off of the crankshaft, but you were already going to have this parasitic loss anyways. But now it's less because there's less weight necessary, and the air pump acts as its own resistive as if it's weight. Okay? And so at the top and the bottom, because I offset it further all over to the left and down, then my up and down with the crankshaft for the double wrist pin then has its regular connecting rod, but then it's angled off to the right, but it's at top dead center. But then like that double wrist pin gives it enough of an angle clearance that allows for it to still go up and down with the piston head being very much in line and center. It'll go over from top dead center. It'll swing like it's at near its 11 to 1. So it'll go up and then over. And then this wrist pin will elongate as inertia and then momentum forces go up to its top dead center for complete compression. And then it allows for it to overturn a little bit both ways, but then there have to be spots where it can't do that any further. And so I get a longer crankshaft, crank lever effectively. But then because of the double wrist pin, then compresses the right way. It then moves over the piston rod over further, and so it's now, instead of angled inwards left towards where the crankshaft's top dead center is, it then moves over, and then it's now angled in more in line. You want it directly in line basically, because it'll shift that piston rod straight over to the right. And so, because it'll do clockwise and then counterclockwise with the connecting piece to the double wrist pin, and so that shifts it straight to the right, and that means as it shifts over on the compression or power stroke, it then gives it much more torque directly in line to the furthest crank angle it can have for direct push down at that very 90 degree, and I actually gain an advantage on the bottom half towards bottom dead center. So there's no one at the door, so there's just someone else. But that also means I gain that power stroke at the top, as well as the bottom half at the past 3 clock position for the crank. But then that's also why these other, offset to that angle too, because I have to offset that for the crank, or further over for the balancers, which is why that's an air pump now balancing crankshaft. Okay, which then sends it to a reservoir. Okay, so this is compressed air, but it's really just moving compressed air. So it's not like super compressed, but it's still compressed to a degree. It's really just moving into a cylinder that then goes into the regular throttle body. So low RPM, it's not going to do much, and then this will make up for it. And then we have like a standard tube after that's this version of an air intake, which is separate Okay, so that has to be separate, and then this goes into the standard low RPM to somewhat medium RPM, uh, tube, which is the air intake manifold will eventually go into where the valves and ports are. Okay, so that means two air filters. Okay, right, and then that sucks in from one side, and then it goes, for the regular air intake, it'll go through, and then we have the standard uh, water to air exchanger, which will go towards the front, and then those are just a tube with like straight lines that are have fins on them that allow for you to have the water go from top to bottom and then drain off into the water to air intercooler exchanger thing that they call whatever it is, and that's a pump. But it's like that's because that crankshaft's hot. Okay, like crankshaft oil is usually pretty warm. It's right next to the damn engine, so like you gotta cool it. So like this gives me a longer cooling duration, and then I have regular air that goes into it as well, which so this gets pumped into that cylinder, so that regular air goes through the water to air intercooler exchanger, and then this will get pumped into just before that, and so like that's a one-way valve now just for the regular air, and this will eventually pick up to the point where it actually starts to become much more of a pump, and then you'll gain more compression, more pressure as the like any other supercharger does as the crankshaft gets faster. All right, so it's a supercharger, but then it's a balancing supercharger off the crankshaft, which is also less weight, and then also happens to be uh, able to to give you better balancing forces because of the way it works. Okay. Now it also gains more torque for the given double wrist pin and offset that you have to have now, which is also one of the reasons why like a regular engine block normally doesn't have this. So I built like what is effectively a girdle that takes this and then offsets it down, and then we give you proper crankshaft rods, and then the air undulator pump for for that, and then like that's the two separate things that then give you the water to air intercooler exchanger, right? And then now you have the whole kit and caboodle as an upgrade, which then allows for you to get much more out of a standard engine would ever have, especially when you can immediately start two-stroking for a very high efficiency, two-stroke by the way, with port injection, and then ignition, which still has compression, and then same thing, even greater because you can change the timings even further down for exhaust, before you need to like actually have all that clear. So you'll have the exhaust start, and then you'll eventually have that intake. So it's like it can be further down towards bottom dead center. So you gain more of that force as actual compression, because now I gained back that bottom, half of that power stroke back a little bit before it ultimately needs to go back up for compression, right? Uh, Now I have a supercharger. The reason why I don't really like it is because often I have to change the roller bearings, and I still have to lubricate and all this other stuff, and I have to have the water to air intercooler, and I have to combine them into one single tube with that valve. All right, like that one way valve, and it's like that's great for lower RPMs up to about that maybe 2200, maybe 2500 RPM. The undulator doesn't really get very good, or the supercharger doesn't get very good until it gets much faster, because it's directly tied, and there isn't really much in terms of the sizing of these air pumps, compressor air pumps, to really gain you those efficiencies that you would think should be there, and like because that's greater and greater degrees of air resistance, and so like there's a very specific size that's very much tailored to your connecting rods, wrist pins, and all that for balancing. And anyways, the girdle just shifts it off down and then over to the left, right? And then we have another version of the the casing for that pump and everything in the sump. So it's basically yeah, that has to be bolted on like any other thing, same normal stuff, but like that's why the exhaust, which this is okay. So real quick, I figured out a way to turn the exhaust into direct to your crankshaft flywheel kind of thing, increases of, instead of like pushing more energy through into more amounts of air, because I already have air, and more amounts of fuel to be able to gain that, because I already did that. Well, now that goes as exhaust into a think torque converter. It's not a torque converter. Straight up, immediately, it's not. But a torque converter goes in between your crankshaft and your transmission, right? Think that. So the exhaust, let's say it was a V8. It's all four of them into a 8 divided area for like an outside of a donut style sort of looking thing that's like a torque converter, but those are where the blades are, which then each one of those go into their own individual versions of a diffuser, I suppose, or whatever, but they're just meant to have like a pack of turbine blades with stators. And so what that stator does is it seals it until it gets to the right RPM, and then it'll open up the next one, and then it'll open up the next one. And so there's only 3 blades, and they're fairly large and they're fairly wide with multiple blades. So think about one blade is a blade pack. And so this has like a standard, length, meaning height, and then width, which means like, let's take your palm width and then like add like the second palm width. But now we're going to have like a secondary blade that's connected to this one, but it's slightly lower and then slightly closer, or slightly further out. And so it's like having 2 to 3, in this case I use 3 of these. An RC test flight on YouTube happened to do a wonderful test on an airplane, and it's a way to create greater degrees of lift. Well, in this instance, that's exactly what captures more of that exhaust pressure into energy. And once the stator moves the correct amount, which means like the spin has ultimately moved that, because that's okay. So the way it moves, it is like a torque converter, but it's not really. It's more of like a 1-to-1 like coupler, but then it needs to hit a certain speed, like a torque converter. So it works like a torque converter, but then it's like more like a coupler. Yeah, but then that pressure goes out and then moves the stator to go back in, or more specifically, there's like a rocker arm. Right. Anyways, that moves it up. Well, no, okay, so you can move it up, but I use the move it in approach, because like there's a version of a hollow axle that I use that then that can go in, and that allows for an opening into the next one, and then that'll allow for that to spin up, and it'll do it again. And so as it spins, it'll gain more and more amounts of conversion of the heat and pressure from the exhaust into direct to crankshaft and transmission degrees of torque and of horsepower, like a 1-to-1. And so it reduces parasitic loss, right, to like standard things that are on your serpentine belt or something. But more specifically for me, it's like, it's a fairly efficient way of capturing that energy into direct increases of power to your powertrain, your drivetrain. And so that means I'm able to gain, depending on the RPM and the speed, which will have inertia, and so it eventually will close off those spots, but it won't be for a little bit to be able to do that. So it'll eventually close the other 2, and then it'll just go back down to 1 at low RPM. So it's like you get the supercharger, which will give you more air, but it's not super efficient. It's not like a really high, step up gear type of supercharger. It's more of a just directly in line with your crankshaft. Then I gain a turbo from the exhaust, which is not really a turbo. It's a turbine system that directly drives it to the crankshaft, like a torque converter, but it's not converting torque because it's not converting the crankshaft. It's like a coupler now that converts the exhaust pressures into direct to your crankshaft energy, which is like its own version of a coupler. Then this adds to that for the torque converter style. So it's like that's the coupler, and then this adds more pressure to that coupler area, which then gains you the extra oomph to your transmission. Right? Now, that then gives you the, for what it's worth, because electricity gets turned into extra heat and greater amounts of better burn, or complete burn, right? And then I have better air and better fuel mixing, more air to also give you, and faster air to give you for volumetric efficiency. It's colder, denser air, all right, for lower, medium, and high, and that can give you scavenging for a two-stroke process, which then gives you the other extra of the exhaust increase of heat, but then also increase of that coupler to torque converter style design that allows for a greater degree of captured energy that offsets, hopefully, that torque, or horsepower specifically, and torque loss of the supercharger, although that was already going to be parasitic loss to begin with when it comes down to balancing. And I got rid of your primary, secondary, and tertiary. Tertiary is twisting motions, which is why those twist. They gimbal a little bit. Not just go from side to side and up and down. They also twist a little bit, but that's fine because they're a roller. It'll be just fine with how that works and slides and everything. Right. On that. Okay, right. Right, and they slide up and down just a scotch, which is like a Scottish yoke, but then that's the bearing that's there for roller bearings, and then a bearing on the inside. So that allows for it to go up and down, and essentially allows for it to pivot while doing that, and it makes it much more efficient in terms of balancing out forces, but also balances the undulation for the air pump. That's the supercharger. Now, that is the complete upgrade package. This is like fucking stage 7 or whatever, I don't know. It's like you got heads, you got camshaft upgrade, you got an air intake, I suppose, if you wanted to. Now granted, I also have an air intake manifold, which that's a whole other story, but think it has directly like tube side on, directly straight, like in line parallel, so it's like, right from the front for the intake manifold, straight off of the water to air intercooler, right? And then that also has a separation that goes towards the bottom, and then it goes and fires up, because I found that to be the cheapest and easiest way to take up some of that in a V8 here, little area, and then that allows for, because it's a curve at the top that goes to a parabolic spike in the center that then has a slight degree of widening at the tip that allows for it to go towards the two middle, and again, it's like this is curved to go towards the four really middle parts. But then that, for the double flute, I use double flutes. Okay, so like double flutes are the big part. Right. So this is a longer double flute, all right, that has little feathers. I like to call them feathers. Take your fingers. There's space in between your fingers. Those are the slots. Well, they go off to stators at the very ends that are shaped to head together with the plenum, but then have an elongated oval that allows for, as a pressure wave goes up and out, to spin and get captured into the secondary larger flute, kind of like a donut, that then gets curved in towards the center where the feathers are and the stator is. Right, and then on the inside, longer stator, I ended up figuring out today, actually, that it'd be really cool if I had these little spiky waves that are in line. So, like, think not spiky waves, just think like I carve into the flute, like a divoted area, and then like there's an overhang with slight little channels and grooves on that overhang. Then it has like a little wave guide. I think the shroud, the rear of a jet engine, where it has that little wave guide. Same kind of thing for that, but then they're spaced wider and then basically non-existent where the final feathers are. What that does is it traps, because now that plenum that I talk about for these heads, which have all these things that are in the inside of it, well, the stator is still there too, where it has the elongated hole inside of the stator. So as the pressure wave goes from as the valve closes up and then out, and then it gets started to be dragged along the sides by the stators and then spun, and then same thing for the next stators, and so a lot of it gets stuck in the wider part, which is sealed, so it does not connect in any way to the top or the middle flute, the top middle flute, right, but it's spinning, which gives him a degree, or not him, me, stator, valve, or flute, funnel area, that spins, and that's a pocket of energy. It keeps compression there. Then that then has those little, spiky kind of wave, whatever things. Anyways, point is, that's where the little channeling and dimpling and so on allows for it to then be dragged, and then tries to keep it. And then the center is still going to go through, though. It's going to bounce off that area. But remember I talked about the fingers and the feathers? Well, there are curved, so it widens, and then towards the insides, all right, from the rear and the front, have these little, flat styles of fingers or feathers that are in line with the travel and direction of airflow. All right, so the bottom just goes up, and then it still gets curved in because those little flat fingers that are aiming towards the center, all right, are then going to have those little gaps, which then have these little channels, or vortex, no, it's not vortex, they're like little tiny wings, basically, but they try and grab and then suck in air into the flute, right, and try and trap it. Anyways, the rest of it gets sent because of the larger at the top parabolic curve towards the center, towards that spike. Then those have another version of the inside goes towards the outside with those little same finger feather things with the slots. But in this case, there's no grips, there's no wings, they're just straight slots. And what that does is it goes up and out, it'll try and redirect that pressure out towards the outsides, but it goes towards the center like a V8, where it'll redirect and crash off of itself and then split down towards the sides. So, think about it this way, that directs towards the top here, which is kind of like the inside part, back towards the outsides, but then also helps it with the centers too, for the firing order, depending on the firing order you have, right? And then the outsides then help the center out. And so it keeps a large amount of compression in the intake manifold, and then uses that oscillation pressure wave to then further help out and potentiate all of the given cylinders ports for intake ports. All right. Finally got there, but that's the intake manifold, and then that's still the same kind of tube with the one-way valve for the low end RPM, and then eventually that will close off as that pressure gets built up, and then it's just working off the supercharger, which is the teardrop shaped with little feathers, or not feathers, fins, heatsink fins for the water to air intercooler, so like water's going to flow through that, and then it'll dump off into the actual radiator, which is another version of that, which is larger, but then that goes off into the intake manifold. So then now you have the understanding of why it's well, that's a lot less restrictive, because that has to be wider to allow for that to be the same size of the full diameter of all of the ports, or well, ports, but the valves. Okay, so specifically the valves have a certain size. I mean, it's 1 to 1. That's not good. So you need a scaling of that's 1 to 2. Then that's got to be from 2, or well, I forget what it was, but it's that scaling, and then to the next scaling of the large, where all of those added up, and then you multiply by 2. Or more specifically, because we're dealing with volume, we deal cubing, or if you don't want cubing, I do it to the power of 4. Specifically because the to the power of 4 scales it properly in terms of keeping pressure with the flutes, but that's for the inside intake versus the flutes, which are to the power of cube, that kind of thing. And then eventually you get to. Anyways, point is, the correct scaling of diameters of the intake allow for better air flow, air velocity, and achievement of reduction of resistance, right? Because like that, those are air resistant areas, and so you need to reduce that kind of thing, right? Then same thing with the exhaust. The exhaust has a degree of these portings for it's wider where the ports initially, and then it kind of technically gets smaller, but then it has these little flutes, those little channels that we groove in there, and then that allows for it to be wider technically, even though its pressure wave won't really notice that. It'll just speed out faster, which gives us, even though it's smaller, it gives us a degree of increased scavenging. But then it goes into a wider intake, equaling tube header, by the way. We have to do that into the torque converter coupler thing for exhaust. Right, so that's wider, but then it has to bend. And so like that's why it was like either up or directly perpendicular or a little bit down. So obtuse, 90, and acute. Now, I forget what the angles are, and we can't do any angle. So like you have specific angles that you have to buy, that you would make in these manufacturing techniques I'm talking about, right? But that way, because it goes from wide, but then we do the same kind of grooving with, actually in this case, little wave guide, like so channels, grooves, or fullers, depending on they're just divots, elongated divots. But then we have another version with those little divots on the inside of that, which then have the wave guides that I was talking about, the wavy undulations, which allow for like a dimpling, but then it's a faster degree of dimpling, and so it sucks it in on the turn, and then we have the same channeling, or like corrugations that are, angled with the direction of flow, creates a pressure pocket, high pressure pocket, with these, in this case, just straight through grooves that are there, that then allow for that to still have very good flow at the tips, but then it creates a pressure volume that then allows for that to turn more easily. Now, while it's wider there, it also means that the inside diameter then turned more and flowed faster. It also changes the oscillational pressures as they all get captured and not try and go to the port, the exhaust port. So then that goes off into, you guessed it, hopefully direct straight into the turbine. So it's a turbine, exhaust turbine, that's the torque converter coupler thing. Right, like it's like it's that kind of thing. And so I've already described that a little earlier, but again, it's just moving. So it's like a coupler, and then we add in more flow with the exhaust spinning those turbine blades, and then the second and then the third pack, and so it captures it more efficiently for the given blade size and angle that's there, that we ultimately have, and which I've already just described that. I don't want to go through that again, but then that allows for you to have your transmission and all the rest of it that works very, very efficiently for the given, like you already have parasitic loss for your weights for secondary, primary, and tertiary balances. Well, now that's a supercharger. If you're going to have those losses, might as well just make it a supercharger. Now, same thing for this exhaust. Well, the exhaust, I can flow it very efficiently, but that's uncaptured energy. which now turns into captured energy, which makes it more efficient. It also acts like, oh, I don't really care, if I'm being honest, because I can change the degree of diversion and the degree of angle. And so, like, different exhaust pressures will give you a different degree of increased load on that. And so that way it can scale linearly with the tri-scroll style turbine as it eventually spins up the next one and next one. So you get that part, but then that's the diversion, meaning the fluid flow rate. So that way it doesn't just dump all of it immediately, and then you get a huge spike suddenly. Like turbo just kicked in, turbo lag just went really, you know what I mean? You don't want that. So it's like you want it to scale from very low RPM all the way up to the very highest RPM that you have, and gain all of that as much as you really reasonably can, anyways, into your torque converter turbo coupler thing that's now going on. And then you have fins on the outside of that, so that way, like, you can cool that degree of heat and hydraulic fluid that's got to be used. And so that way you're going to have that moved a little bit further out than where the exhaust is, and insulate, blah blah blah. Point is, you get the cooler for that, which is good. You want that. Then that goes off to your catalytic converter, which I don't know why you would need it, because I burn it so damn efficiently that I don't think that you would need one for what it's worth. But they require it, so you would use it, but you wouldn't need it because I'd have almost next to no, or not almost next to no, but I'd have fewer nitric oxides and fewer carbon monoxides, and overall more carbon dioxides because it burned more cleanly, and H2Os because it burned more cleanly, and less oxygen coming out, which is great, which means we're not running very lean, because you'd be able to burn a little bit, run a little rich, and then you'd be able to get that energy back. So you'd be much closer to a perfect stoichiometric mix ratio. So, all told, more efficient, more powerful, 4-stroke to 2-stroke engine upgrade platform that would be far better balanced, and use, depending on the ECU setting, less to more, because I can gain back that heat pressure and from the exhaust into that torque and horsepower gained, and so I can use less with the electricity and then better cleaning burn to allow for a better outright efficiency at different RPMs for that power for eco mode, using retarded timings of our valves, and less lift, and so we can use less fuel, and we can tone back from 2-stroke to a 1-stroke to gain all of that increased efficiency and still have really good power without having to sacrifice fuel use, which is great. All right. Now, that is why I warned you that this would be longer, and that is the end of this. Thank goodness. It's done. Please give it a like. Please subscribe. Please follow. Please, please, please do that. This is a very unique design that I think could be easily done without even my manufacturing and all that. It'd just be a slightly different style of extrusion processes and casting and finishing processes, or billeting and CNC processes. But personally, I prefer mine just because it's more efficient in all aspects. And that's the end of this. Hopefully you would be able to understand and grasp what it is I'm saying in terms of the air pump, the better fuel efficiency, The reason why the spark is better, the reason why the burn's better, the reason why the valves are better, the reason why the crankshaft's better, the reason why the exhaust, all this stuff is just better, right? Bye.